what we're going to do is we are going to talk about graphing equilibria and changes in equilibria. And then I'm going to give you, I'm thinking minimum a half an hour, at least half an hour, to either work on your lab, which is due at the end of class, right? I'm going to hand out a practice assignment so that you can practice things if you want to, or you can work on your major assignment. In the last 15 minutes of class, we're going to do a Le Chat quiz. Is that okay? All right. Okay. So I'm going to go. You don't have to, but I'm going to go all the way back to the beginning. To the very first, very first page, the bottom of the first page. There are only three things that we can do to an equilibrium. You can change something's concentration, so add or take away something. You can increase or decrease the pressure, or you can change the pressure by changing the volume. Those are really the only things that you can do. Now, when we change a concentration, that means we're adding one thing or taking away one thing at a time. Okay? That's important for us to kind of understand. When we change the temperature, are we adding any matter to an equilibrium? Are we adding any material? No. If I put my test tube, okay, here's the second part, the part B of our lab yesterday. If I put this solution in a hot water bath, am I adding material into this test tube? No, I'm not. Okay? You're not actually adding or taking away anything. Okay? And then if I change the pressure, change the volume, by changing the volume of this system, does that affect all the concentrations, or just one concentration, or none of the concentrations? What happens? All of the gaseous molecules, right? All the gases in here. Okay, so that's going to be important. We're going to come back to that a little bit later. So now I will go all the way down here. And so this is just a guide, right? Self-explanatory guide to help you analyze disturbances in a graph. There's three changes: concentration, temperature, and volume or pressure. And they have very, very, very different looks to them, okay? When we add one substance, if I add a substance, this is either going to cause a change in the concentration of only one thing immediately. So let's take a look at my equilibrium right now. What do you want to do? Do you want to add something, or do you want to take away something from this equilibrium system? Let's add something. What do you want to add? Do you want to add A, B, or C?
B.
A. I heard A first, so we're going to add A, okay? So, okay, our disturbance is that we're going to add A. At that point, we're going to add A. Sure, no problem, whatever. Can you see how at this point in time we've established an original equilibrium, right? Now, if I add A is in red, so I'm going to add A. What's the only immediate change that happens to our equilibrium system? A increases, right? Mm-hmm. How would you show a really, really, really fast increase in A's concentration, Jada? A line straight up, starting where A left off. So this line is going to increase real quick. Is that the only thing you've added or taken away to our system? So that's the only immediate change. This is going to be, right? When you add or take away something, you should see one spike. Do you know what I mean? No? Okay, we'll talk about that in a second. Okay, by adding A, yeah.
Oh, sorry.
Okay, by adding A, which direction is our equilibrium going to shift? Is it going to shift to the right, or is it going to shift to the left?
Right.
It's going to shift to the right. Okay? And the reason why that is, I've talked to a couple people about this today. The reason why that is, these equilibrium arrows, they literally mean forwards rate of reaction and reverse rate of reaction, right? By adding A, you've increased the concentrations of your reactants. So that means you've got a much quicker forwards rate of reaction. So have we thrown the system out of equilibrium right now?
Yes.
Yes. They're no longer equal. The forward and the reverse rate are no longer equal. Which rate, which direction of reaction is winning right now?
The left.
The forwards reaction. And so which way is that indicating the system should shift?
Right.
To the right. Does that make sense? So that's why we say when you add something, it shifts to use it up. Okay? Now, when we shift to the right, what that means is we're taking our reactants, reacting them together, and we're turning them into products. So what will happen slowly over time to A? It'll decrease because we're reacting A and B together to turn it into C. So slowly over time, this will decrease, B will decrease, and C will increase. We're turning A and B into C. So let's draw that. Let's draw that on our graph. A is supposed to decrease over time. So we're going to curve A down, and then it's going to flatten out. Is A ever going to get back to where it was in the beginning?
No.
No. You've added A, so it's always going to be higher than where it was in that equilibrium. What's going to happen to B?
Same.
It's going to decrease. And because the coefficients are the same, they're going to decrease by the same amounts. So we're going to decrease by the same amount. And then C, what's going to happen to C?
Increase.
It's going to increase. And it's going to increase by the same amount that these decreased. So let's take a look at this. Can you tell the difference? When you look at this graph, can you tell the difference between an immediate change and a slow, gradual change in our equilibrium? Which one of these had an immediate change? A. You can tell because it spiked up at the beginning, right? Everything was honky-dory, right? Equilibrium, 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 and then all of a sudden, that concentration spikes up. And because it spikes up, then we get a slow, gradual change in every other concentration. So could you look at this graph, and could you tell me what caused the change in equilibrium? Yeah, obviously we added A, right? And if we would have taken away A, right? If we would have taken away A, it would have looked like a spike down, and then it would increase slowly over time. Does that make sense? So when you add one thing or take away one thing, there's only one spike. So a change in concentration should only have one spike in it. Okay, what about a change in volume? Let's take a look at this. When a container changes volume, all the concentrations of all of the gases change. Only the gases, right? The concentrations of the substances will either spike up or spike down. What do you want to do? Do you want to increase or decrease the volume of this container? let's increase it. Because what's easier for you to visualize? Is it easier for you to visualize a decrease in volume or an increase in volume?
Increase.
I would venture a guess to say that for most people, when you decrease the volume, that's easier to visualize. What happens to all the particles in a container of gases if you decrease the volume? Do they all get closer together or further apart? Closer together. So what does that mean? An increase or a decrease in the concentration? An increase. If things get closer together, they're more concentrated, right? If you increase the volume, what happens to those particles? Do they get closer together or further apart? Further apart means a decrease in the concentration. So what we're going to do, at this point, we're going to increase the volume of our container. Okay, let's take a look at our equation. Are they all gases? So this will affect all of them, okay? All right, sure, no problem. By increasing the volume, what do you do to the concentrations of these things? They all decrease, and they all decrease immediately. We take our container, and it's like we're taking our box and we're blowing it up immediately. We don't slowly increase it, we go boom. So all of the concentrations jump down, every single one of them. A spikes down, B spikes down, C spikes down. That's a very fast change. Okay, so let's try and figure out which way the equilibrium is going to shift. Let's see if it's going to shift to the right or shift to the left. How are we going to do this? What happened to the concentration of A immediately?
Decrease.
It decreased. What happened to B?
Decrease.
It decreased. What happened to C?
Decrease.
It decreased. Where did we have more of a decrease?
We don't know.
On the reactant side. So we had more of a decrease on the reactant side than we did on the product side. Where is our equilibrium going to shift to?
Left.
It's going to shift to the left. If we have a decrease, the equilibrium will shift to make more of it, right? So, if that means we're shifting to the left, are our reactant concentrations going to slowly rise or slowly drop? Slowly rise. So both A and B will slowly rise. Will they ever get back to where they were before? No. They will slowly rise. And what will happen to the concentration of C? It will slowly drop. Now, when you have changes in volume, how many spikes are you going to see? How many immediate changes in concentration are you going to see if you have a change in volume?
3.
Well, maybe not 3, but
If we have the
all of them. They all either spike up or down, okay? They all spike. Is that okay? Can you immediately tell the difference between a change in volume and a change in one thing's concentration, us adding or taking away something? Yeah, okay, all right. So now let's do a change in temperature. What do you want to do at this point here? Do you want to increase or decrease the temperature?
I have a question about volume.
Okay.
Volume is, can you also say it was a change in pressure for
Yes.
change in volume? So if it increased the volume, say you decrease the pressure and you still get it right if it was like a written?
That's fine. Yeah, I'm okay with that because for the most part, you will see this as a multiple choice question on the diploma exam or a numeric response, and the responses will be given to you. You have to choose the correct response, right? So I'm fine with that. If you said a decrease in pressure or an increase in volume, they mean the same thing as far as I'm concerned. But I'm just telling you, in reality, what's the easiest way to change the pressure? Volume. So that's what it actually causes it. But okay, what do you want to do? Do you want to increase or decrease the temperature? Dominique's saying increase. Okay, we're going to increase the temperature. So, what are you adding to this system? You're not adding temperature, you're adding energy, right? And the energy causes an increase in temperature. So you're adding energy. Which way is the system going to shift? It's going to shift to use it up, so it's going to shift to the left. Now, what did I do immediately? What happened to the concentration of A? Nothing. Immediately, what happened to the concentration of B? Nothing. And immediately, what happened to the concentration of C? Ugh. So nothing, nothing, nothing. And immediately there was no change. How many spikes, how many quick changes in concentration do you see? 0, none. Okay? Well, what's slowly going to happen because we're shifting the equilibrium? What's going to happen to the concentration of A? A is going to slowly increase. What's going to happen to B? B is going to slowly increase. And what's going to happen to C? C is slowly going to decrease. Because we increased the temperature. Perfect. So how many spikes do you see in a temperature change? 0. No spikes. Are we good? So your only options, when you're looking at a graph, your only options are one thing spikes, everything spikes, or nothing spikes. Those are your only options, right? Let's take a look at some graphs. And I want you to take 30 seconds. Don't talk to anybody else. You try and tell me what happened to the system at that point. Okay, what do we think happened? First of all, was it a change in temperature? No. Why? Because one thing spiked. What substance spiked in concentration? HCl. Did we add HCl or did we remove HCl? Okay, so because of this, we know that we removed HCl. We took it out of the system. Okay, not all of it, but we took some of it out of the system. Let's see if that makes sense. By taking HCl out of the system, which direction would this equilibrium shift?
Right.
It would shift to make more of it. If you take it away, it'll shift to make more of it, okay? So what should happen to the concentration of HF slowly over time? If we shift it, it'll decrease, and that's exactly what we see. What should happen to the concentration of HCl? It'll increase. Immediately it decreased, but because we're shifting to make more of it, it slowly increased over time. And what happened to CCl2F2? It'll increase as well. And it'll increase half as much as HCl increased. Why is CCl4 not on here?
It's liquid.
It's a liquid in a heterogeneous reaction, and we don't care about liquids in heterogeneous reactions. That makes sense? Okay, one more thing. Take 30 seconds. Try and tell me what happened at that point in the graph. Okay. Was this a change in, did we add or take away one thing? No. Did we increase or decrease the volume?
Yes. Yep.
Because if we change the volume, what immediately happens to all the concentrations? They spike. Every single one of these should spike, right? Now, what I'm seeing here is, remember, if something spikes, I want everybody to pay attention to this. If something spikes, that means it's going steady, 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 bam! It immediately drops. And most of the time, like not all the time, but most of the time, it'll do the opposite of what the spike was, okay? Here, I don't see any spikes. I see a slow gradual change, a slow gradual change, and another slow gradual change. So what do you know happened here? A temperature change. Now there's two options. We could have increased the temperature or decreased the temperature. Which one do you think it was? If I increase the temperature, we'll shift to the left. So what will happen to O2? It'll go up. If I increase the temperature, it'll shift to the left, and so O2 will go up. Is that what we saw happening? Nope. So we must have decreased the temperature, because that would shift to the right, and that would cause both of these things to decrease and this thing to increase. Does that make sense? So what did we do at this point in time? I promised you there would be no math involved, but very conceptual, right? This whole 15.2 is the exact opposite of 15.1. Okay, 15.1 is basically all about math. This is not basically all about math. Are we okay with that? Okay, we are right on schedule. So, what I want to do is I want to talk just for a second, just for a tiny little second about the lab, okay? And then I'm going to give you at least a half an hour to work on this. And then I'm going to give you 15 minutes to do the Lechat quiz, okay? The Lechat quiz, for the most part, is tell me what happens to these substances if this happens, right? Or analyze this graph and tell me what happened at this point in time. Remember, one spike, you add or take away something. All spike, change in volume. You have to figure out if it increased or decreased in volume. And no spikes is temperature, because you didn't actually add anything. You didn't change any concentrations, right? What I'd like you to do is I'd like you to take out your lab. Okay. What's the only part of the lab that I'm marking? Analysis of part 1, right? So the cobalt complexes. Okay, I'm not going to talk about the cobalt complexes, but what I am going to talk about is the thymol blue. Okay, here we go. I've got some thymol blue, and what color is thymol blue? Oh, well, all right, okay. So what does that mean? What do we mostly have in our solution? Where are we? Well, if this was red, does it make sense that we would have mostly red? If this was yellow, does it make sense that we would have mostly yellow? And if this was blue, does it make sense we would have mostly blue? Are we okay with that? All right, perfect. Now, this is a really weird thing. This is a series of equilibria that are all connected. Now, the red turns into the yellow. And what can the yellow turn into? Blue. So it's almost like a zigzag. You can go either this way or you can go this way in your equilibrium. Is that okay? So let's try and think about this. This is blue right now. If I increase the concentration of acid, which way will this equilibrium shift? Towards the left. So what will we make more of? The yellow, and we'll make less of the blue. Is that okay? And that's exactly what I'm going to try and do. And now don't fault me. Please don't fault me if I do this incorrectly, okay? It's actually a little bit hard to do. I'm supposed to be wearing safety glasses. That's fine, whatever. This is only going up on YouTube. So I'm going to add some hydrochloric acid, drop by drop. Oh, see that? Okay. I'm going to add this drop by drop. Oh. Oh, interesting. Okay. So did we kind of turn yellow?
Yes.
Yeah, it's definitely not red, right? Okay, we kind of turned yellow. So now we're mostly yellow. Just trust me on that. We're mostly yellow. So you can think of ourselves as either here or here on the equilibrium. It's kind of both places at once, okay? If I add more acid, I shift this even more that way, but that doesn't do anything because we're already yellow, okay? If we're here and I add more acid, which way am I going to shift? To the left, and we're going to make a red mixture now. So let's try this. I'm going to add one more drop. Can you see how it's orange on the bottom where the acid hasn't been yet, and red on the top where it is? Son of a gun. Oh, that was way too much. Way too much. So did we turn more red?
Yes.
Yeah, for sure, more red. Now, so that's moving the obvious direction, right? So now we're mostly red. Okay. How can I shift it back that way? I can add something that will take away acid. If I take away the acid, we'll shift back that way. Well, what can take away an acid? A base. And so I will add a base. Drop by drop. Ooh, it turned immediately a little bit blue. But let's shake it up. Yeah. Ooh, definitely turned more yellow. Oh, come on. I believe in you. You can do this. Yeah, that's way better. And if I keep going, right, we're going to keep going along that zigzag, and we turn blue. Does that make sense? So this is a more complicated equilibrium, where if you go this way, or you can go this way along this equilibrium. Are we okay with that? All right. Now, you have a half an hour to work on your lab, which is due today, but it's not due today, okay? If you need Monday to do it, then that's fine. Hand it in on Monday. That's whatever. I'm going to give you a practice assignment. The practice assignment is for practice, not for marks. The key is already up on Google Classroom, and you can work on your major assignment. So I'm going to walk around handing that thing out, okay? We're going to have our quiz in almost exactly a half an hour.